Hello friends, welcome back to Positive Approach. This is Nitesh. Today we will going to discuss about circular motion, which is chapter number 3 of unit 3. First of all, we will discuss some key point of this chapter, and after that we will do some numerical on the basis of this formula. So without wasting any time, let's start. Our first key point is centripetal force. Centripetal force is always directed toward the center of the circular path, and it is given by F is equal to mv square divided by r, where r is the radius of that circular path, v is the velocity of the car, and m is the mass. And this centripetal force given by F is equal to mv square by r. This is our first formula. And centripetal force always directed toward the center of the circular path. And our next force is centrifugal force. Centrifugal force is directed away from the center of the circular path. It is away from the center of the circular path, and centrifugal force is not a force of reaction. It is a fictitious and pseudo force. Which force? Centrifugal force. Yes, centrifugal force is fictitious and pseudo force. Our fourth important key point is centripetal force needed for circular motion. Yes, centripetal force is needed for this circular motion. Here centrifugal force is not necessary for the circular motion. It is not needed for any circular motion. Which force? Centrifugal force is not needed, and centripetal force is needed for circular motion. Our next key point is car can negotiate the flat rough circular path with maximum speed. V is equal to under root of mu gr. If the velocity of car on this turn, if the velocity of car at any turn increases by this value, then the car goes outside of the road, and it is the maximum speed of the car on a circular path. Our next key point is saved speed of the car to negotiate a banked road of radius r. For a banked road, the maximum speed of a car is equal to v under root of rg tangent theta, where tangent of theta is equal to v square divided by rj, where theta is the banking angle, and the saved speed, it is the maximum speed of the car to negotiate a banked road of radius r, where theta is the angle of banking. Our next key point is relation between linear and angular velocity. Here v is the velocity is equal to r into omega. This is the relation between linear and angular velocity. And keep in mind, this this banking angle is independent of the mass of the vehicle, mass of the body. Yes, this banking angle is independent of the mass of the body. Our next key points are: what is angular velocity? Angular velocity is the angular displacement by time, and its unit is radian per second. Yes, angular velocity is the angular displacement divided by time, and angular velocity is given by 2 pi by t. And in term of frequency, this angular velocity is given by 2 pi nu, where this nu is equal to 1 over t. These are the expression for angular velocity, and its unit is radian per second. Our next key point: weight of moving car over a convex bridge is less than the weight of same car on the same bridge when it is in rest. Yes, the weight of a moving car with the convex bridge, let this is a convex bridge and here the car, and it moving with velocity v. Weight of a moving car over a convex bridge is less than the weight of the same car on the same bridge when it is at rest. If this car is at rest on this bridge, then the weight of car is equal to mg if the car is at rest. And when the car is moving with velocity v, then the force applied on this car is this mg minus r, okay, which is equal to, now this is the part of a circular path, so it required centripetal force which is equal to mv square by r. This is implies this r is equal to mg minus mv square divided by r. Here you see that there is a some factor which is minus from its weight, so it is clear when the weight of a moving car on a convex bridge is less than the weight of car is at rest, because when the car is at rest its weight is mg, and when it is moving on this convex path its weight is mg minus mv square by r. So this is less than that of mg. I hope this concept is clear to you. Why the weight of car on a moving convex bridge is less than that of the weight of a car on this bridge at rest. Our next key point is centripetal force acts radially inward and the centrifugal force acts radially outward. Our next key point, minimum speed of the lowest point of a loop is equal to under root of 5gr. Yes, when there is a loop of this type and here is a cycle, it moving with velocity v, then at this point its velocity is under root 5gr, and at this point and the maximum height at this point the velocity is under root of gr. These are the safe velocity for any cyclist or any object. And speed at highest point of loop of a car is v is equal to under root of gr. This is the velocity of a car or a cyclist or any object at highest point in a loop is under root of gr, and the lowest point is under root 5 of gr. These are very important result. And our next key point is weight of a moving vehicle over a convex sharp bridge is always than that of its actual weight. Our next key point, what provide the centripetal force to a car taking a turn on the level road? What provide the centripetal force of a car taking a turn on the level road? The force of friction provide this centripetal force of a car to taking a turn on level road. Our next key point is a body moving along a circular path such that its speed is constant. A body moving along a circular path with its speed is constant. Should there be a force act on a body? Yes, there is a force which act on a body at every point of this circle. That force is called centripetal force. Yes, that force is called centripetal force. Whatever the speed, whether the speed is constant, there will be a force, and that force name is centripetal force. These are the important key point of this chapter, circular motion. Now we will doing some important example or important numerical of this chapter. Our first numerical is a car is moving with 72 km per hour on a flat circular road of radius 10 meter. Can the car negotiate the curve with this speed? We know that the negotiate speed of car over a road, over a flat road is under root of mu gr, where mu is the coefficient of friction. Now velocity v is equal to, a car is moving with velocity. The velocity of car is 72 km per hour, which is equal to 72 multiplied by 1000 divided by 36, which is equal to 20 meter per second. Now the velocity of car is 20 meter per second, and car can negotiate, and the negotiate speed, the maximum speed of the velocity is under root of mu gr, which is equal to under root of mu here 0.3 and g is 9.8. For simple calculation we take it as 10 into r, and what is the radius? Radius is 10 meter, which is equal to under root of 3 by 10 into 100, which is equal to under root of 30, which is equal to under root of 3 into 10, and this value is approximately equal to 5 point something meter per second. Now here you see that the maximum velocity is 5 meter per second, but car is moving with this velocity of 20 meter per second. So it cannot negotiate the curve of this speed. It if this car moving with the speed of 20 meter per second, it will definitely goes outside of the road. And here its maximum velocity is, for this mu, value of this mu is 5 meter per second, 5 point something meter per second. I hope this numerical is clear to you. Our next numerical is a stone weighing 50 gram tied on one end of the string is to be rotated in horizontal circle of 1 meter with the speed of 5 meter per second. Calculate centripetal force. What we have to calculate? We know that the formula of centripetal force, F is equal to mv square divided by r, where m is the mass of body, v is the velocity, and r is the radius. What is the mass of body? A stone weighing 50 gram. 50 gram into 10 raised to power minus 3 kg, because we have to convert all the system in SI system of unit, and the string is rotated in horizontal circle of 1 meter. Its radius is 1 meter with the speed of 5 meter per second, and its speed is 5 meter per second. And what is its centripetal force? Here F is the centripetal force, which is equal to 50 into 10 raised to power minus 3 into 5 5s are 25, which is equal to 125 into 10 raised to power minus 3 into minus 2, which is equal to 1.25 Newton. This is the force, centripetal force. This is the centripetal force when a stone is weighing 50 gram tied to one end of the string. So I hope this numerical is clear to you. Very easy numerical. Our third numerical is a vehicle. A vehicle moving with 36 km per hour may negotiate the circular banked road 5 meter. What should be the minimum balancing angle of the road? We know that when the road is banked, then its maximum velocity to negotiate is under root of Rg tangent theta. We have to calculate here the minimum banking angle of the road. Squaring both sides, we get V square is equal to Rg tangent theta. Here tangent theta is equal to V square divided by Rg. I hope this is clear to you. Now substituting the value, what is V? V is 36 km per hour. We have to convert this into meter per second. 36 into 1000 divided by 3600, which is equal to 10 meter per second, which is 10 square divided by r. What is the radius? Banked off road with 5 meter. Here radius is 5, and take G 9.8 and take it approximately equal to 10. Now which is equal to 10 into 10 divided by 5 into 10, which is equal to 5 2s are 10. Here tangent of theta is equal to 2. Now you can calculate this theta by using the log table, and this theta is approximately equal to 63 degree. So minimum banking angle of this road is theta is equal to 63 degree. I hope all these numerical are clear to you. This is all about our third chapter, circular motion. I hope this is all clear to you. Thank you and have a nice day.